Okay, in this lesson, we are going to talk about a method called trig substitution. And when we have expressions involving the square root with either a squared minus x squared under the square root, or x squared minus a squared under the square root, or x squared plus a squared under the square root, we'll be able to use this method. And the point of this method is to set up a triangle and then rewrite our expression, whichever one it is, in terms of trig functions. And then we can use our knowledge of trig functions, either a direct formula, or we can use the tricks that we learned last lesson to then integrate. So when we have this expression here, where we have the square root of a squared minus x squared, this is how we're going to set up our triangle. And you can double check it and make sure it works with Pythagorean theorem. If I take this squared plus this squared, it's going to be equal to this squared. Now that we have our triangle set up, I am going to create an expression for x. So x, if I look at this angle right here, sine of this angle is going to be opposite over hypotenuse. So that's x over a. Now when I rewrite that, solve for x, I get x is a sine theta. So this is what we're going to use to rewrite our integral when it's in terms of the square root of a squared minus x squared. So if we let x be a sine theta, then dx is going to be x cosine theta d theta. Now, when we replace x with a sine theta, so that's going to go in here, I'm going to square a sine theta. So I'm going to get the square root of a squared minus a squared sine squared theta. Here's my dx. I'm going to replace my dx with a cosine theta d theta. And then I'm going to simplify this as much as possible. If I factor out an a from under the square root, that gives me an a squared on the inside, and then in parentheses, I got 1 minus sine squared. I can pull the a squared out from underneath the square root, and that becomes an a. And when I multiply it with this a here, I'm left with this a squared. Now, underneath here, I'm left with the square root of 1 minus sine squared, and that's this here. And then I'm left with cosine theta d theta, that's here. Now, this 1 minus sine squared theta can be written as cosine squared. And then when I take the square root of cosine squared, I just get cosine. And then when I multiply it with this cosine, I'm still left with cosine squared. So now we've shown in general what happens when we rewrite the integral of the square root of a squared minus x squared, where a is a constant. We can rewrite it like this. So I have a squared times the integral of cosine squared d theta. And then here we can use our methods that we learned in the previous section on how to integrate powers of cosine. All right, now let's look at an example of integrating something with this form. So we have the integral of the square root of 9 minus x squared. Because it's in this form, we're going to set up our triangle so that we have the square root of 9 minus x squared on the adjacent leg, and then we're going to have x as the opposite leg and 3 as the hypotenuse. And it's 3 because a is 3. This is our a squared, which is 9, so this is going to be a is 3. Now when we check it, we should have that the square root of 9 minus x squared quantity squared plus x squared should give me 3 squared, and that works. So we know we got our triangle set up correctly. So if I isolate the x, I get that x is 3 sine theta, which means that dx is going to be 3 cosine d theta. Now this is exactly what we were doing before, just in general format. Now we're doing it with some actual values here. in for A. This is what we did before in the first part of the lesson where we were doing it generically. Now we have a value for A, which is 3. So I'm going to take and put my x squared in here, which is 9 sine squared theta. And then here's my dx, it's 3 cosine theta d theta. Now, if I factor out a 3 from under the square root, and then I multiply it by this 3 here, that gives me this 9 here. I'm left with under the square root 1 minus sine squared, which I can replace as cosine squared. And then when I take the square root of cosine squared, I get cosine times this cosine gives me cosine squared. So now we have rewritten our integral in a form that we know how to integrate. Now we have this set up so we can use the methods from the previous lesson where we know how to integrate powers of cosine. So we're going to use the double angle formula for cosine, and we're going to rearrange it for the cosine squared. So we can substitute this in for cosine squared. So here was my cosine squared, and I'm substituting the 1/2 plus 1/2 cosine 2 theta, d theta. I still have this 9 out here. That was my a squared. I'm going to distribute that 9. And now when I integrate, I get 9/2 theta plus, I'm going to have 9/2 sine 2 theta, and then using the chain rule in reverse, I have to divide by the derivative of this inner function, which is 2, and that's where this 4 comes in. It was 9/2, so it was 9/2 sine 2 theta, and then I have to divide by 2. So that's where this 4 comes from, and then I have the plus c. So now I have to go back and rewrite everything in terms of x. So here's our triangle. I know that the sine of theta is x over 3. So if I want to figure out what theta is and replace this, I'm going to use inverse sine. So theta is going to be inverse sine of x over 3. So we substitute this in for our theta. So now it's in terms of x. Now I have this plus 9/4 sine 2 theta. So I have 9/4. And what I'm going to do is I'm going to use the double angle formula for sine. The double angle formula for sine is 2 sine cosine. And then I'm going to use my triangle again to figure out what that is in terms of x. So here's my 2 from the formula. My sine is x over 3. That's this here. And then cosine is adjacent over hypotenuse. So it's this over this. So there's my cosine, here's my sine, here's my 2. So I'm going to go ahead and replace that in here. Then when I clean it up, I can knock off the 9s, I can make that 2/4 a 1/2, and then my final answer will be this, where I have 9/2 inverse sine of x over 3 plus x times the square root of 9 minus x squared all over 2 plus the constant. In our next example, we're going to do another example involving the expression, the square root of a squared minus x squared. Here's what we want to integrate. We have the square root of 4 minus x squared all divided by x. So our a is going to be 2 in this case. 2 squared is 4. So here's how we're going to set up our triangle. So our adjacent leg is going to be the square root of 4 minus x squared. Our opposite leg is going to be x, and our hypotenuse is 2. So we're going to get the sine is x over 2. So when I solve for x, to make my substitution, I get x is 2 sine theta, which means dx is 2 cosine theta d theta. And so I'm going to substitute in for x this 2 sine theta. So that's going to give me 4 sine squared theta because I have to square the x. So this was 4 minus x squared. And when I substitute in the x, I get the 4 sine squared theta. And now dx is going to be substituted for the 2 cosine theta d theta. And then x is going to be 2 sine theta, so that's going to come down here and replace x. So now I can take the 2 from under here, the 2 squared, I'm going to pull that out as a 2. And when I divide it by this 2, I get 1. And then I have 1 times this 2. So after cleaning up these constants, I'm just going to have a 2 out in front here. What's left over is going to be the square root of 1 minus sine squared, which I can write as the square root of cosine squared. And when I square root cosine squared, I get cosine, and cosine times this cosine gives me cosine squared. And then, of course, I bring down this sign in the denominator. So this is currently what we have after we do some cleaning up. Now we still need to do some rearranging so we get it in a format that we know how to integrate. So we can use our Pythagorean identity to replace cosine squared with 1 minus sine squared here. And then I can split up my fractions. So this 2 is still a constant. We pull that outside. So I have 2 times the integral. And when I split up these 2 fractions, I have 1 over sine minus sine squared over sine. 1 over sine is cosecant. Sine squared over sine is just sine. So now these I can directly integrate using our formulas. So I have 2 times the integral of all this. So that's going to give me, when I integrate cosecant, I get 2 times the natural log of cosecant minus cotangent plus 2 times the cosine of theta plus my constant. Now we have this completely integrated, but we still need to write our final answer in terms of x. So looking at our triangle, this is not my best picture, but that should be 90 degrees. But here's our picture. So I need to replace cosecant, cotangent, and cosine with expressions in terms of x. Cosecant is the reciprocal of sine, and I know sine in this case is x over 2, so when I take the reciprocal, cosecant is going to be 2 over x. So I'm going to replace this cosecant here with 2 over x. Now I know cotangent is cosine over sine. So here's sine. Cosine is adjacent over hypotenuse. And so when I take this divided by this is what I get. I get that cotangent is the square root of 4 minus x squared all over x. So that's going to go in for cotangent here, right? That was this. And then my last step is to do 2 times cosine. And we already said cosine is this. So that goes in here. I can get rid of these 2's and clean it up. And then so here would be my final answer with everything in terms of x. For this next example, there's 2 different ways that we can integrate this. We're going to walk through both ways. One, we can use U substitution, and the other way we can use trig substitution. If I rearrange this integral by writing x to the third as x squared times x, and everything else gets copied down, and I let u be 1 minus x squared, then I get du is negative 2x dx, which means I can replace x dx with negative 1/2 du. So this inside here becomes u. I can replace x dx, this and this, with 1/2 du. And then x squared, if I rearrange this for x squared, I have that x squared is 1 minus u when I rearrange this for x squared. So then I can replace x squared with 1 minus u. So now I have everything in terms of u. And I've rewritten this in a way that's easy to integrate because we would just use the power rule. I would first clean it up by distributing this u to the 1/2. And then we can just use the power rule. So we have this negative 1/2 Just carry that over. When I take the integral of u to the 1/2, we get u to the 3/2 divided by 3/2. When I integrate this, I get minus u to the 5/2 over 5/2. And then, of course, my plus c, clean it up a little bit so I don't have complex fractions, and replace the u's back with x's. Go back and resubstitute, and we get this as our final answer. Now, if we use trig substitution, we're using a different method, but it's still the same integral, so we should get the same answer. So using trig substitution, here in this case, my a is 1. So I'm going to set up my triangle as the square root of 1 minus x squared on the adjacent leg of the triangle. Here's my opposite side, that's my x, and here's my hypotenuse, which is just 1. So my sine theta is going to be x over 1, which is just x, which means my dx is going to be cosine theta d theta. So everywhere I see x, I'm going to replace it with sine. So in here, my x squared now becomes sine squared theta, and my x to the third now becomes sine to the third. And when I take this and I simplify it, that becomes the square root of cosine squared. And when I take the square root of cosine squared, I get cosine. So I have cosine times cosine, which is cosine squared. So now I have a product of sines and cosines, and we can use that method that we used in the previous section. So when sine is raised to the third power and cosine is raised to the second power, what you want to do is you want to break down sine to the third as sine squared times sine, and rewrite sine squared using the Pythagorean theorem. So this is my sine squared that I rewrote as 1 minus cosine squared. Here's my third sine, and here's the cosine that I just pulled down here. Now, according to our method that we used from the previous section, when sine is 3 and cosine is 2, we let u be cosine, so du is minus sine theta d theta. So anywhere I see a cosine, I'm going to replace it with u. So this becomes 1 minus u squared. This becomes u squared. And then I can replace sine theta d theta with a negative du. So that's this negative and this du. Now when I distribute this, I get u squared minus u to the fourth du with this, make sure we bring that negative over here in front. And then when I integrate, I get negative u to the third over 3 plus u to the fifth over 5 plus our constant. And then I go back in and resubstitute. For u, I get cosine to the third times negative 1/3 plus cosine to the fifth, 1 times 1/5 plus my constant. And because cosine theta is the square root of 1 minus x squared, that's this up here, right? Cosine is adjacent over hypotenuse. So adjacent over hypotenuse in this case would be the square root of 1 minus x squared. I go back in, and everywhere I see cosine, replace it with 1 minus x squared square root. And so now everything is written in terms of x, and here is my final answer. So as you can see, both methods yield the same result. So now we're going to talk about integrating expressions that have the square root of a squared plus x squared in them. And it's going to be very similar to what we did previously. Our triangle is just going to be set up differently. So our adjacent side is going to be a, our opposite side is going to be x, and our hypotenuse is going to be the square root of a squared plus x squared. That way, when we do tangent, that's opposite over adjacent, I get the tangent is x over a. And so when I solve this for x, we're going to get x is a times tangent. And so we're just going to use that to make our substitution. And then this is the problem solving strategy that I copied out of the book if you'd like to use it as a reference. So looking at our first example here, we have that we want to evaluate the integral of dx over the square root of 1 plus x squared. So here's our triangle set up. A in this case is 1. And so we're going to get the tangent of the angle is equal to x over 1, which is just x. Now when we take the derivative of x, we get secant squared theta d theta. So I'm going to replace dx with secant squared d theta. So this dx becomes secant squared d theta. And then underneath here, I'm left with 1 plus x squared, and we're substituting tangent in for x. So this becomes the square root of 1 plus tangent squared down below. And again, we're going to use one of our Pythagorean identities to make the substitution. 1 plus tangent squared is equal to secant squared. And when I square root secant squared, I get secant. So now I have the integral of secant squared d theta over secant, and I'm just left, when I reduce this, the integral of secant theta d theta, and we can directly integrate this using one of our formulas. So when we integrate secant theta d theta, I have the natural log of secant plus tangent, and then my plus constant, and then I have to rewrite this in terms of x. So looking back at our triangle, here was our triangle from above. We know that secant is the reciprocal of cosine. So when I look at this, cosine is adjacent, which is 1, over the hypotenuse, which is the square root of 1 plus x squared. So here's my cosine. So when I take the reciprocal to find my secant, I get the square root of 1 plus x squared. So secant is going to get replaced down here with 1 plus x squared. Now sine is x over the square root of 1 plus x squared, because it's opposite over hypotenuse. And since we're trying to find tangent here to replace something in terms of x, remember the tangent is sine over cosine. So I'm going to take this over this and simplify it, and I'm going to get x for tangent. So my final answer is going to be the natural log of the square root of 1 plus x squared plus x plus c. Here's an application of when we would use trig substitution. And in this example, we're going to find the arc length of the curve y equals x squared on the interval from 0 to 1/2. So if you remember the formula for arc length, x over the interval from a to b, you're going to integrate the square root of 1 plus the derivative squared. And so in this case, my derivative is 2x. So when I square that, I'm going to get 4x squared, and that's what I'm going to substitute in here. So to find the arc length, I'm going to go from 0 to 1/2, and I'm going to integrate the square root of 1 plus 4x squared. Now it's in that format of a squared plus x squared. So we are going to set up our triangle like we did in the previous example. Here's my a, here's my x. In this case, it's 2x, not just x, because we have 4x squared here. And then we're going to have, for the hypotenuse, the square root of 1 plus 4x squared. So when I find the tangent of this angle, it's going to be opposite over adjacent. So tangent is equivalent to 2x over 1, which is 2x. When I solve this for x, I get that x is a half tangent. And then when I take the derivative, I get the dx is 1/2 secant squared d theta. So I'm going to substitute 1/2 tangent theta in for this x here. And so that's going to give me 1/4 tangent squared. And the 1/4 with this 4 is going to give me 1. So I'm just going to have tangent squared here. Now I'm going to replace dx with 1/2 secant squared d theta. So that goes here. And I have to remember, now that I have translated this into thetas rather than x's, I have to remember to change my limits since this is a definite integral. So before I went from 0 to 1/2, now I'm going from 0 to pi over 4. Using our Pythagorean identity, I know that the square root of 1 plus tangent squared gives me secant. And when I multiply it by the secant squared here, that gives me secant cubed, and this 1/2 comes out in front here. Now, in the previous lesson, I made a note and I told you to keep track and make a note of what the integral of secant to the third is, because rather than working all through that to find it again, we know what the general formula is for this. So using the information from the previous section, we found that the integral of secant to the third, theta d theta, was equal to this big mess right here. That's all of this right here. So we want to now integrate this. So we're going to evaluate this whole big expression here. We're going to evaluate it from 0 to pi over 4. And remember to bring down that 1/2 in front. So we have 1/2, this big mess here, inside here, and we're going to evaluate it from 0 to pi over 4. Now when we do that, we're going to get 1/4 times the square root of 2 plus 1/2 times the natural log of the square root of 2 plus 1. In this last example, we're going to go through the situation where you could evaluate an integral that involves an expression in the form of x squared minus a squared, square root of that. And so here's your general problem solving strategy that I pulled from the book as normal. You could use that as a reference. And then down here, you'll notice for these, you have two possible reference angles for when you're evaluating a definite integral. You have to make sure you keep track of which reference angle you're using depending on your value of x and a. So keep that in mind. So let's go on and look at our example. It says find the area of the region between the graph of f of x equals the square root of x squared minus 9 and the x-axis over the interval from 3 to 5. Now, since we have to find the area of the shaded blue area here from 3 to 5 under this function, we're going to set up our area as the integral from 3 to 5 of the square root of x squared minus 9 dx. So this is our triangle that we're going to use for trig substitution. When we have this format where we have the square root of x squared minus a squared, we're going to use so that the adjacent side is your a, your hypotenuse is your x, and then the opposite side is going to be your square root of x squared minus a squared. In this case, our a is 3 because we have 3 squared here. So this is how we have our triangle set up. So that gives us that the cosine of the angle is adjacent over the hypotenuse, so that's 3 over x. And when we solve that for x to make our substitution, we get 3 over cosine theta. Now this can get messy using fractions, so it's easier to rewrite this as x is equal to 3 secant theta. And then when we take the derivative of x, we get 3 secant theta tan theta d theta. So this is what we're going to use to substitute for dx. So the x squared is now going to become 3 secant theta squared, which gives us 9 secant squared theta. And then, of course, I bring down this 9. The dx becomes the 3 secant tan theta d theta. And then because now we have this in terms of theta, I have to make sure that I reevaluate my limits here. So if I plug in 3 here to figure out what my theta is, I'm going to get the inverse secant of 1, and we know that that's 0. That's a nice easy one. This one isn't so easy, so I would just leave it as is, and we'll use a reference triangle later to figure that out when we evaluate. Now, when we simplify this, this 9 and this 9 can be factored out. And then when I pull it outside of the square root, that gives me a 3. And then when I multiply it by this 3, I'm still left with a 9. Now under here, I'm left with secant squared theta minus 1. And we know that that's equivalent to tangent squared theta because of our Pythagorean identities. And then when I take the tangent squared and square root it, I get tangent. And then when I multiply it by this tangent here, I get tangent squared. And then this secant can just come down. So I carry everything else down. I got tangent squared. I got secant squared left over after I multiply my tangents. And then I get d theta. Now, I know that tangent squared is the same as secant squared minus 1. So I'm going to rewrite tangent squared as secant squared minus 1 and distribute the secant. When I do that, I get secant cubed minus secant theta. And of course, I still have that 9 that I brought down. This secant to the third theta, we figured that out already a couple times, what that's equivalent to when I integrate. So that's this here highlighted in pink. We've already figured out that formula. So I integrated secant to the third to get this right here. Secant theta, I can integrate that directly using one of our integration rules. So that's minus the natural log of secant theta plus tan theta. And I have to bring down the 9, and I have to evaluate this all over from the interval from 0 to inverse secant of 5/3. So here's my limit. So I still need to evaluate that. Now, when I plug in 0 to this, everything drops out. So this is just 0 when I subtract at the end. So really what I need to focus on is this. So I set up another triangle here so that I can figure out what my values are. Since secant is hypotenuse over adjacent, I set up my triangle. Here's my hypotenuse, here's my adjacent. I know that this is a 3, 4, 5 triangle. So now I can use this triangle to evaluate my secant and tan. So this 9, when I multiply it through, that gives me 9/2. And then secant theta, that would be 5/3, right? Hypotenuse over adjacent. Tangent is opposite over adjacent, so that's opposite over adjacent, so that's 4/3. So this 9/2 comes down here, this is 5/3, this is 4/3. Bring down the minus, bring down the 9/2 that I got from taking 9 times 1/2 here. Bring down the natural log, and then I do the same thing here. Secant is 5/3, tangent is 4/3. And so all of that information I got from creating this triangle. Then when I clean this up, I end up getting 10 minus 9/2, the natural log of 3. And remember, when I subtract what I get when I evaluate it at 0, that whole big mess is 0. And so all I have to do is figure out what this is. And when I put that in on the calculator as an approximation, I get 5.056. So this is my exact value. This is my approximated decimal value.